Okay, good morning. So we continue for this chapter. So in today we will first to talk about the charge neutralities. So the electron, this charge neutrality condition is used to determine the thermal equilibrium electron and hole concentration as a function of the impurity doping concentration. So we have to first to come out with this charge neutrality equation, which is expressed as here, N0 plus Na minus is equal to the P0 plus the Nd plus. And the idea is very simple. If you look at the band diagram here, so we have the top one is a conduction band, and then the bottom one is a valence band. And now we both consider the impurity as the doping as a donor and acceptor. So we have the donor energy level and we have the acceptor energy level here. And in this case, that we all know from the last week, we already knew that the dopants in the donor level and the acceptor level, that possibly some of them will be ionized. So if we consider the ED here, then we could, for example, have such amount of the donors here, and then part of them can be ionized to contribute as electrons. So this will become contribute as an electron here. So that's what we call this as ionized donors. And also similarly, we also have certain ionized acceptor in the acceptor energy level, which this ionized acceptor in the end will contribute as a hole in the valence band. And then in here we call this as a ionized acceptors. And also we have to consider that there are some part of the donors not being ionized, which is shown here, which is unionized. So these can be unionized donors and also the unionized acceptors. And also without any consideration of the dopants, no matter for the acceptor or donor, actually we still have to consider the electron and holes that's being crossed the band diagram due to the thermal. So that's why we also have the thermal induced electrons and the thermal induced holes. So that's a completely picture for the compensate semiconductor. Compensated, what does mean compensated? It means that this is semiconductor material that both has a acceptor and a donor at the meantime, and this is a complete picture showing the compensating semiconductor with ionized and unionized donors and acceptor here. So we have this equation where our N0 and P0 are thermal equilibrium concentration with electron and hole in the conduction band and valence band. And also, we know that the ND is a concentration of electron in the donor energy state, and PA is a concentration of holes in the acceptor energy state. So therefore, we can start to have the following equation where the ionized donor ND plus is equal to the ND minus the small nd. So this is a concentration of the ionized donor. Also similarly, we can have the Na minus the Na minus is equal to Na minus Pa, and which this is ionized acceptor. So with considering this ionized donor and ionized acceptor, so then we just put in here, this here, and this here, and in the end, we can have this one. So that's a consideration of the charge neutrality, and also in the meantime, we consider the compensating semiconductor that with both ionized and unionized a donor and acceptors. And this is a full equation, and once we consider the complete ionization, which we can simplify the equation as shown here. Once we consider the complete ionization, then the ND and PA are both 0, and therefore the previous equation can be simplified as the following. And also, we already knew that the N0 times P0 is equal to the Ni squared. That's the equation where we have already derived it previously, and then the rest of things just matter with to try to solve this equation, and then so we put everything here. So this is a very general equation, and that can be easily solved, and in the end the result is try to derive the thermal equilibrium electron concentration. So in the end, actually the purpose is that we try to have the equation that both consider the N-type doping and P-type doping. So if you look at the previous slide, the Venn diagram, once we consider the compensating semiconductor, it's a very general case that you can probably both have the P-type doping and N-type doping at the same time. And therefore, we want to understand if we have a P-type doping, N-type doping at the same time, what is exactly the electron concentration. So this is a case that very often that we will meet in our semiconductor device. For example, if you look at a typical MOSFET here, so we all know the MOSFET is first to fabricate on the certain type of a concentration substrate, for example, the P-type substrate, and then we will dope in somewhere the P-type substrate in somewhere start to have the N+ doping, where these regions are as a source and drain, and the rest is dielectric and the gate metal. So if you try to think about in the more detail, so you will start to realize this is a region whether you both have the two different dopings. First, you have a P-type doping. You also have an N-type doping. So then if we want to very precisely to determine the concentration in this region, we need to start to apply this equation. So this is the region that we both have the P doping and then the N doping here, which the P is Na, right? So this is in this formula, this is Na, and this is Nd. So now, if we want to very precisely to determine this region, this is a region that we call, sometimes we call the compensating semiconductor, but to be honest, the compensating semiconductor is not a term that we use very often. Usually we don't use. But in the beginning, for introduction of the concept, we probably will use in this term, but in the end, it's just a piece of a material that you can both have a P-type and N-type doping, and then we want to understand what exactly the thermal equilibrium concentration. So that's why we spend the time to derive this equation, because in the end, this equation is going to be very useful. Of course, for the most of the case that because we will dope the N+ in this region. In most of the cases, we will dope very high concentration N-type doping, so then your Nd will almost dominate everything in here. But still, there's a slightly difference between the Nd and then the N0 here. So if you want to precisely determine, then you need to use this equation. So similarly, we can consider to calculate the thermal equilibrium hole concentration in the piece of semiconductor that both have the P-type and N-type doping. And in the end, we have the P0 is equal to Na minus Nd over 2 plus Na minus Nd over 2 So the equation are very similar, just reverse the direction, reverse the position of Na and Nd, then we got the thermal equilibrium hole concentration. So, of course, the derive of this equation along with several assumptions, and then also in the beginning is a little bit difficult to understand what's the purpose we have to do this calculation. But in the end, I hope that with this explanation, you will probably get more sense that this equation is actually useful, but also it's very straightforward to understand. We just try to calculate the place that both have the two type of doping. Okay, so that's just some more additional small concepts. I think most difficult part is we already go through, and then this is just some small detail of the additional concepts. So that's also possibly there's a redistribution of electron when donors are added, and then you can see that there's a possibility of the donor electron can be recombined with some intrinsic hole. So that's just some possible scenario. Just you need to, you don't have to really pay too much attention, but sometimes just keep in mind that there's some possibility that can be happen in this line. Okay, so the next one is that now we have the so many equations we derive. And then, as I say, the purpose of the equation is not going to confuse us. The purpose for this equation just try to support our physics-based understanding, because sometimes we have the physics-based sense, but for scientific consideration, we need to have a certain equation to support our physics analysis. So in this slide, we will talk about how we can determine the position of Fermi energy level, which we starting from this equation that the N0 is equal to NC exponential EC minus EF minus over KT. And then with this equation, we do the very simple mathematics, so we can get the EC minus EF is equal to the KT natural log NC over N0. And we do some assumptions that in this case, we consider our doping, N-type doping is much larger than our intrinsic concentration, and therefore our N0 is very close to our doping concentration, and therefore we can have this equation EF minus EFI is equal to KT natural log N0 Ni here. So this equation is actually tell us that if your N0 is larger, and that means that this we can use a different N0, and then you will cause a different Fermi level energy position. So this is a conduction band, this is a valence band, and now we try to determine the Fermi energy position, which we have the EF, and also we have EFI. Okay, so similarly, we can also derive the Fermi energy level depends on our Hall concentration here, and therefore we can have this one. So the concept here is very simple. With this help, all this equation help, and then we can start to analyze the Fermi energy level with respect to the different doping concentration. So as the doping level increase, the Fermi energy move close to the conduction band for the N-type material and close to the valence band for the P-type, as shown here. This is here is N-type, here is a P-type. So as we dope, doping concentration is higher, as you see here. Then actually our EF will be close to our EC, and also as our Hall concentration is higher, and then our EF will close to our EV. So now everything can be either analyzed by our physics-based understanding, or can be easily validated by the equation we have. And also, another additional concept is we have to be aware of that the intrinsic carrier concentration Ni is a strong function of temperature. So therefore, the EF is a function of a temperature as well. And once temperature increase, the Ni increase, and then EF will close to the intrinsic Fermi energy, as shown here. So this is 1000 over T. So this suggests that toward the left is a high temperature, toward the right is a low temperature. So from this one, we can understand that if we have the higher temperature environment, actually the Ni will increase, and then the EF will close to our intrinsic Fermi energy. And also, at a higher temperature, semiconductor material begins to lose its extrinsic characteristic and begins to behave more like an intrinsic semiconductor. Because now, if it goes to the higher temperature, then actually your all characteristic will be dominated by the Ni, because the Ni will increase, and therefore your material will be, everything is determined by your Ni. And also, another interesting thing to know that if we go for very low temperature as to the right here, in the end we will figure out that you go to the very low temperature, and then it is possible that all our donor and acceptor cannot be ionized. So that's why we have this what we call the partial ionization. The partial ionization suggests that your donor and acceptor cannot 100% to contribute as an electron and hole. So that's why we call it a partial ionization. And sometimes we also call this phenomenon as a freeze out. So this freeze out and then the partial ionization down to the low temperature is become very crucial challenge if we want to use our semiconductor in the quantum application, especially for quantum computing. In the case of quantum computing, we need to down to the extremely low temperature, below 4K, sometimes below 1K. And in that case, we will face the issue that our doping cannot be fully ionized. And so we need to also consider this problem as well. Okay, so that's a summary. So in this chapter, we are talking about semiconductor in equilibrium, and then now we expand from the pure intrinsic material to the one that we have the extrinsic doping. Extrinsic doping, that means we start to dope our semiconductor material with additional P-type and N-type doping, and therefore we need to understand the concept about the ionization. So we have the most of the case in silicon we have a completely ionization, but however in other semiconductors this is not always true, and then we use the charge neutrality try to start to estimate the electron and hole concentration, and this is a very important equation that we will use very often. Normally the very often here is referred to the class in this class for the homework for the exam, because later if you start to do your own research, it's sometimes very limited. We will still use a hand calculating for this equation. We mainly use some software. There are already many software can help us to determine the doping concentration. But anyhow, go to the fundamental side. You still need to understand how and why we can use these equations. Okay, so finally we finish the discussion under everything still in the thermal equilibrium. But what we are interested in is definitely not the one that only under the equilibrium. As you already knew that when we try to operate our device, we always do a different kind of a bias. We give the voltage in the different terminal. Sometimes we even give the current here, and we try to put it in a different environment, low temperature, high temperature. And therefore, it's also very crucial to understand the semiconductor under any additional force, which we consider this will cause a non-equilibrium case. And before we go to the non-equilibrium case, first let's just spend the time to discuss with carrier transport. We want to understand that what kind of the transport mechanism. The carrier here is related to the electrons and holes, and we want to understand that what would be the general transport mechanism related to the electron and holes. So the first one is thermal motions. So even in the case without additional electric field, carriers are not at rest, but possessed with a finite kinetic energy here. So then in this case, electron and holes move at a certain velocity. This is what we call as a thermal velocity. But it's not in the simple direction. So that means that this actually, the electron and hole will move as a thermal velocity, but what we consider here is this carrier will move in this kind of zigzag motion. So zigzag motion, it means that this carrier will be moved in this way. like a simple direction to the right. But in general, if you look at the overall behavior, it looks to the right. But if you look at in the detail, they actually will goes back and forth. So that's what we call the zigzag motion. And this zigzag motion is mainly due to the collisions or scattering. Because of we definitely will have some imperfections in the crystal. So this imperfection in the crystal will cause the collision and then the scattering. But overall, the thermal velocity will be equal to 0. So that's the first one, is the thermal motion. But what we are actually interested in is definitely not in the consideration of the thermal velocity, but actually we are interested in is one that once we give a bias, and then more generally we call it electric field. So sometimes electric field is normalized with the voltage, so that can give us more like the fair way to judge the bias, because of the electric field is normalized with a certain distance. So in this case, the first one we would like to consideration is once we give a certain electric field, there's a phenomenon that we call the drift. So the drift is a motion caused by an E field. And clearly the drift is usually only happen when voltage are applied to a piece of the semiconductor device. And then in this case, that will cause a drift. And with considering this additional movement caused by the electric field, and then we give the term that how to quantify this carrier behavior, this carrier velocity, that we call as mobility. So the mobility is a very often term that we use to quantify as a very specific carrier that under the different bias, and then the different material will have the different electron and hole mobility. So let's just go step by step. So first one, the drift momentum gain between collision is equal to the force Q times the mean free time. So here we can start to have this equation. The left hand side is a momentum, and the right hand side is the electric field force, and then the Q, so equal to the force. This is a force E times Q, and also times mean free time here. And also we can start to simplify this one, become this one where we define the mu p is equal to the Q tau MP over MP, and the tau MP here is a mean free time. And the MP here is the effective mass. And also the term here, why we call the hole mobility, is because of this P suggests this is related to the hole. So that's why this is a hole mobility. So similarly, with the same consideration, we can for sure to derive the equation, which is mu n is equal to q tau n over mn, where this is considered as an electron mobility. And this is electrons. So, consider this the mobility in the electron and hole, so then we can start to have the equation try to consider the carrier drift. Especially here, we are interested to understand this carrier drift will contribute how much the current. So therefore, we call this as a drift current. So in here we consider the whole drift current, which can be expressed by this one, and also the electron drift current can be expressed by this one, and therefore the total drift current is we have the total drift current, just a summary of the electron and holes drift current, which is Jp drift plus the Jn drift. And then in summary, we can have this one where is equal to mu n plus mu p electric field, where we both consider the electron and then the hole in the sense of the carrier drift here. So I believe so far the calculation is still very simple. I think in this chapter we only have such simple calculation like shown here. But the main point is, as I already said, that the main point for this equation is not going to confuse us, just try to help us to understand the physics inside here. And now we can understand that the drift current is highly dependent on our electron and hole mobility, which means that the different electron and hole mobility in the one material can play the important role. So for example, in the case of a silicon, the electron mobility is around 1,300, and then the hole mobility is around 400. So we can foresee that there is the huge difference mobility between the electrons and then the hole mobility in the silicon material. So that means if we try to fabricate the transistor, in the transistor we all know the characteristic that we are interested in is a drain current versus a gate voltage, which we have the drain current versus gate voltage here. And in the case with electron mobility dominate, where will be in our case with NMOS. So in the case, why we call this as NMOS? Because this is a case where the electrons inversion in the p substrate, and then the main carrier cause current here is an electron. So that's why we call this as NMOS. And this is exactly the normal case that we most talk about. If we try to look back for the previous slide, when every time we try to explain the MOSFET, we always use the NMOS as an example because that's more straightforward and easily can be understood. But of course, since we have NMOS, this also suggests that we might have the MOSFET that we call as a PMOS. In the sense of the PMOS, this is the case where we consider we use a N-type substrate, and on top of N-type substrate, we start to dope the P+. We dope the P+. And similarly, the rest are the same. We put a dielectric here. We put a gate metal here. And the only difference here is that if we consider the PMOS, this is a typical PMOS. In the case of the PMOS here, what we need to do is apply the negative gate bias. Because in this case, we want to induce a hole. The only possibility to induce a hole is you need to apply the negative gate bias on top. So once you have the negative gate bias here, for sure you will start to attract the holes, and in the end, the holes can be inverted in the N substrate. So in this case, we consider the hole inversion in the hole inversion in the N substrate, and that's why we call this as a P MOSFET here. And the rest of the operation is very similar to the NMOS. We will talk about the details later. Even for the equation are very similar. So, but what I want to illustrate here is that in the case of the PMOS, still our current here is proportional to our hole mobility. And therefore, if we all use a similar silicon material to fabricate the N MOSFET and the P MOSFET, and this will cause a problem that we have a different mobility. So this different mobility suggests that if we have the current for the N MOSFET, something like this one in the silicon, we probably, for the same material of silicon, we only have the whole current as a 1/3 proportion to the N MOSFET, because of our whole mobility is only 1/3 compared to the electron mobility. So that's why you will get a pretty lower drain current if we use a silicon P MOSFET. So that's why people try to look at some new material, try to address this issue. That's why we will come out with a germanium. Because of, as you see, germanium has a 1900 mobility, which is just slightly higher than silicon. So then slightly higher than the electron mobility in silicon. So in this case, if we try to fabricate the P MOSFET using the germanium, then we should be able to get a very good output current. So that's why germanium is very attractive for the P MOSFET. But of course, for the N MOSFET, actually have very good mobility as well. But sometimes for the transistor, we also need to consider the balance of the drain current for the NMOS and PMOS here. So this gives us a certain motivation why we have to implement the germanium in the PMOSFET, in PMOS as our technology here. And also on the one hand, you will see that the gallium arsenide in the first introduction slide, we already talked about that there are some compound materials that are very suitable for the high frequency, high speed communication. And this is the reason why the gallium arsenide is suitable for the high frequency and high speed, is because of the mobility is so high. So this is good for the high speed communication application. So that's why we will consider to use a different material that can contain a different mobility, give us a good new to fulfill our demanding on new technologies. With this consideration of the drift current, then we can also try to wrap up as this drift current as a combination of the N drift plus P drift, which is equal to here Q mu N plus Q mu P E field. And in this case, in most of the time, we also define this term, because this term is only depends on the mobility and concentration. So therefore, we also define this as a conductivity. So this equation will become here. So the J drift current is equal to the conductivity times electric field, and the conductivity just 1 over. So 1 over conductivity is resistivity. So the resistivity is equal to the 1 conductivity. So now you probably get more sense, because the resistivity is a term that you should already knew in the very early time, because that's resistivity is related to the resistance. So now we can have the way to estimate the resistance of one piece of the semiconductor material once we have the doping, once we have the mobility. So here just a summary for the total drift current and conductivity that we already mentioned. And also, therefore, with considering the conductivity, and then actually we can start to make this plot where our conductivity versus the doping for the P-type doping or N-type doping. And then I think it's very straightforward that once we increase the doping, our conductivity is decrease. Sorry, this is in the term here. This is resistivity. This is resistivity. This is not conductivity. This is resistivity. So this suggests that once we increase the concentration, for sure the resistance is decreased. Then we can have the plot like in this way. And this becomes very important when we try to design our transistor, because if you try to look at the schematic of the MOSFET, we have a structure like this here. We have a structure like here, so we all know the left-hand side is a source, which we dope as a, this is a source, this is a drain. And if you try to look the simple resistor network from left to the right, and we will figure out that first of all, there's a contact resistance in this interface, and later we have the resistance in the source region, and we have a resistance in the channel region, and also we have a resistance in the drain region, and then in the end we have another contact resistance. So if you try to calculate the total resistance from left to the right, and then you will have this very simple equation, which will be equal to 2 times RC plus channel resistance plus the source resistance plus the drain resistance here. And from the very basic, we all know that in the normal case, in the lots of case, no matter for what kind of application, we always try to keep the resistance as lower as possible, because in the semiconductor or electronics world, the resistance will cause a certain power consumption, which is not something we want. So in the end, we always want to make the resistance as lower. So then our goal is try to reduce the total resistance. So far, you don't know what kind of strategy to reduce the RC and R channel, because it's something that we haven't talked about yet. But if based on your understanding of the source and drain resistance, if we want to reduce the source and drain resistance, the only possibility is increase the doping. So that's why you will be seeing, that's why the source drain is normally doped as a N++, because the purpose is trying to reduce the total resistance. So that's why, of course, we already draw the MOSFET lots of times already, so you probably already knew the answer. It must be the N+ in the source and drain. But here is the reason why it needs to be the high doping concentration in the source and drain, because in the end we want to have the semiconductor device that gives us a low resistance. The low resistance also suggests the higher current. Okay, so the next one is we need to consider some non-ideal effects, especially we all know in the semiconductor crystals, they are many imperfections. So what happens if there are the imperfections in the crystal? And this imperfection will cause a certain scattering. And there are two main scattering mechanisms. The first one is a phonon scattering. And then the second one is a Coulomb scattering, which is related to the ionized impurity scattering. So we are many have this one. The first one is the phonon scattering. The second one is due to the Coulomb force. So we can have this Coulomb scattering. So the phonon scattering are mainly caused due to the phonons in the, if you try to look at certain some of the solid state physics, solid state series book, then you can find a lot of the description of the phonon. But nowadays, I think you can just Google and then you will find the very basic definition of phonon. So the phonon is as a case where our particle under the vibration. So this is a particle representation of the vibration of the atoms. In the crystal, and because of this vibration will cause the certain sound. That's why we call this as a phonon. It's similar to the kind of the origin of the sound. So that's why we call this as a phonon. And the phonon scattering will cause a mobility decrease with a temperature increase. So this is the conclusion for the phonon scattering. Here we don't do any derive for the phonon scattering. Just show the result is that this has a temperature dependency, where has a relation as shown here. So that's a phonon scattering. And second part is our Coulomb scattering. And this Coulomb scattering is very simple, just because of this repulsive Coulomb force or attractive Coulomb force. So as we all know that if we already have the one negative charge here, which is has a negative charge, and therefore suddenly you have another negative electrons being injected to the right because of two negative charge will have the repulsive Coulomb force, right? So the two negative charge part is not possible. Two negative charge can be close with each other. This is what we call the repulsive Coulomb force. So this negative charge will result that this negative electron will turn in another direction due to this repulsive Coulomb force. And on the other hand, similar things, if we have the charge, which is a positive fixed charge, then also if we have the electrons flow to the right, then for sure this will cause the attractive Coulomb force. That means this negative charge, this negative electron will try to flow in the way that there's a positive charge nearby. So that's we call the attractive Coulomb force here. And in this case, we have the mobility has this kind of the temperature dependency, as shown here. So this is a mechanism related to the repulsive or attractive Coulomb force. So that's why we call this as a Coulomb scattering. So the overall, if we consider these two mechanisms, one is a phonon scattering, another one is a Coulomb scattering, and then we can have this graph that in general that we have the two different temperature dependency, and this temperature dependency will depend on the different temperature range. So in the lower temperature range, we have this Coulomb scattering. In the higher temperature range, we have this lattice scattering. This lattice scattering is just the same as we mentioned. This is a phonon scattering. So, in overall, the mobility can be influenced by these two factors here. But these two factors also will be highly depends on the concentration. In the case with this is high concentration, we can see it's exactly to fit this kind of the model. But with a low concentration, then actually the impure scattering will be limited. So the total scattering rate is the total mobility are determined by sum of this inverse, and therefore the total mobility can be expressed as shown here. Also, one additional the concept we would like to bring your attention is that there is what we call the velocity saturation. So ideally, if we look at the previous equation, our drift current is only proportional to our electric field. But actually, once we go to the very high electric field, we will start to see this kind of velocity saturation. So for example, this is silicon. In the low electric field, the velocity is proportional to the electric field. But under the high electric field, start to saturate. So this is what we call as a phenomenon as a velocity saturation. Okay, we will take a break and then come back later, and then in the next part we will start to talk about another carrier mechanism, another transport mechanism which is related to the different concentration that we consider as a diffusion mechanism. 期末考可能会在也还不确定，怎么样？
就6月9号我要出国，我那天考可以先不要考。
通常我们只会有一次考试，对，我们就是没办法分开考，所以你是6月9号，那你什么时候回来？
礼拜7天的。
OK， 好，那到时候我再考虑一下，看看大家怎么讲，大家的时间。
那哪时候会？
可是现在离期末考还有点远呢，我现在很难决定的，因为我们要看当时的进度。对，我们现在只会讨论到期中考时间。
不会有补考。
不会有补考课，因为这样可能会对其他人不公平，因为这样有些人会先考先忘。对，而且这样我们还要出2个考卷。
所以，不太可能在期末考周考。
期末考的时候考。
期末考周。
期末考周我是顺至几季
？6月16周，6月1号。
6月1号，6月1号可能不太可能。对。
所以大概就是6月9号，是再延1个礼拜。
6月。
就是课程考要的。
对，我们可能不会在6月1号考试，对，因为我不确定那时候有没有办法交完。对。但是如果是5月底考，就太快了。对，5月底考的话，我想应该全部人都不会通的，因为5月底考就太快了。可6月9号，你是6月9号到几号
？9加7。
16号。
刚好16号。
对，可是问题现在我没办法决定，因为现在期中考没考，所以我也不太确定。而且我会 depend 期中考大家的考试的状况，再做决定。OK， 好。
下次。
就是我看到有些是写 H 吧，那有些是 H。
我觉得2个应该是同
一，因为这个差2%。
OK， 好问题耶。这个可是至少不是以这个这门第一门上面叫做算命。对。所以我不知道，因为确实有可能对，没错，2个差2%，对。但是我就是可能是前有些有考虑，有些把前2拍放去哪里或者怎么样。
OK。老师，那我问就这个，前面这个值啊，这些值我们是可以怎么样求出来，或者算出来？
这个你这个值要算的话，就用前这个公式算。
就用这个这个。
对，你要考虑 mean time， 然后 effective time。
可是如果是以实验来说，mean free time 我们求得出来？
实验来说，我们通常只是算到这个叫做 effective 的field effect 对。不会是这个是所谓我们叫做快材里面的别，对，就是但是我们在正常时间我们通常只会算 field effect 就是加压的时候，基本上就用 G 去算 field effect， 对。
OK， 好。我刚就是我们上次开会，对，要讨论这个问题，
所以我们可能要这样，因为这个会被录音。 你先把它的用处先了解，然后跟我讨论一下，我再看。对，然后我们有些我是觉得应该是他们那没有，你说我因为像我在新加坡，这是为什么？就是如果有这个然后我都直接去想，明年那个时候也是定掉，基本上就是因为我们都做过来边，所以我们就想说，我们比较没有就是会有这种医学，比如说如果说对，如果去帮 A 公司开发把这个东西的 process， 因为我对那个对，但是我还是希望可以第一 level 的一些我们要的产品，那 level 就是什么？就是我们可以上一些电子特性，这些电子特性的话，我觉得到时候这些配合就然后就对，然后你所以在问那个钱，然后因为我们第一年有在不到然后说不就是如果要自己的目前没有配置，可是讲英话说，温度没有标法大，每一个区域有没有大，根本就看他们有写，然后就问说在哪里，然后跟哪里有关系。那你还有什么其他事情？就是要提早的时候。我们没有很好，对，没有很好。代理系。OK，那可以先这样子。因为就是那一个分就只有那一次，然后来操作。
刚好是14号早上6点多这样子。14号，对，4月14号。那其他时间晚上？要忘记了，我14、15、16、17。好，那帮我就可以转点，因为我之前缺一门，所以我就不想再上课。对，所以我想应该是
Okay, so we'll move on to the next mechanism for the carrier transport. So in this, we will talk about the diffusion. So diffusion is a process where particles flow from a high concentration region to the low concentration region. So if we have the high concentration particle in this region, and for sure the carrier will try to flow to the right, to the low concentration region, in the end to reach the certain equilibrium. So this is a mechanism related to the diffusion. So for example, if we consider the electron concentration, so the electron concentration has a distribution along the y-axis, as shown here. This is the electron concentration along the y-axis. So this distribution suggests that in this region we have a low concentration. In this region we have the higher concentration here. So therefore we can expect that the diffusion mechanism that will lead to the electron flow to the left. So this will cause an electron flux to the right. And because the electron flux to the right, and that also suggests that our electron diffusion, because the current is defined as a direction similar to the holes, and therefore the electron diffusion current will not flow in this direction, will be flow in this direction. This is because of the current definition is opposite as the electron current. So that's why we will have the electron diffusion current to the right. And therefore, based on this diffusion, based on this concentration distribution, then we can have the electron diffusion current is defined as Q times the diffusion coefficient times the concentration gradient, dn over dx here. So the dn here is diffusion coefficient. So that's the diffusion mechanism cause the electron diffusion current can be expressed as shown here. And similarly, we can also consider the Hall diffusion current. We have the Hall concentration versus our x position, and we have the diffusion profile as shown in here. So based on this distribution, we know that this is a region where has a higher Hall concentration, and this region has a lower Hall concentration. And for sure, based on this distribution profile, we can foresee the Hall flux will flow to the left as well. And this will cause the Hall diffusion current to the left. this will cause a whole diffusion current to the left. This is because of the current is the same direction of the whole current. So in this case, the JP diffusion is equal to, because flow to the left, so we put the minus here, minus Q dP dx. So that's the whole diffusion current. So once we consider the concentration difference, then the carrier will try to flow from the high concentration region to the low concentration region, and therefore that will cause the diffusion, electron diffusion current, and then the whole diffusion current. And then the only difference is just the sign of the direction of the electron diffusion current, and the whole diffusion current is not the same, because once we define the current, we follow the current flow of the holes. That's why we have the one positive and negative difference. So finally, we consider the overall current, where we both consider the drift and the diffusion. So the total current is equal to the total electron current plus the total hole current, and therefore the total electron current can be also divided by the two parts. One is the Jn drift, and another one is the Jn diffusion. And we just put the equation that we already have here, which is equal to Qn mu Ne plus the Q dn dx, the concentration gradient. And also the total hole current is equal to Jp drift plus Jp diffusion, and is equal to Qp mu Pe minus Q dP over dx here. So that's the equation we have already, and we just put everything together here. So we all know that now the current here is related to the concentration, mobility, diffusion coefficient, and also concentration gradient. So these are all factors in the end will influence our current. And let's just look at this one special case that we might have the situation that the semiconductor that is non-uniformly doped with a donor impurity. So in this case, this is a band diagram. This is a conduction band, and this is a valence band. And we now can see the Fermi energy shown here is suggests that the high concentration in the left-hand side and low concentration in the right-hand side. So therefore, we have the electron concentration will be distributed as shown here, because the left-hand side has a high concentration and right-hand side has a lower concentration. And with the consideration of this distribution, in the end we can also start to calculate the certain electron and holes current as well. But in here we won't do the very detailed calculation here, just for your information that in reality there's a possibility that we do have this non-uniform dope concentration in the piece of semiconductor material, but in the end the idea how to deal with this semiconductor material for the electron and hole concentration are the same, the one that we described before. So the next one is that we can also come up with another equation that we call as Einstein relationship. This is a relationship between the diffusion coefficient and mobility. So we consider the case under equilibrium. In the case of equilibrium, that means that there is no current. So in that case, the drift current and the diffusion current, these two put together will be equal to 0 here. And therefore, with a certain further calculation, then we can have this Einstein relationship to describe our diffusion constant. dN is equal to the correlation between the diffusion coefficient and then the mobility can be shown in here. And also this is a diffusion, the whole diffusion coefficient correlate with our whole mobility can be also found in here in this equation as well. So that's Einstein relation. It's a very simple calculation. Just consider how to in the end try to find the correlation between the diffusion and mobility. Okay, so here is a summary of this the chapter. So the chapter here is mainly to talk about there are the two basic transport mechanisms. One is drift, another one is a diffusion. So the drift is due to the electric field, and the diffusion is due to the different concentrations that cause a concentration gradient. So with considering these two mechanisms, so we can finally come out with a total current, which is the summation of the drift current plus the diffusion current as well. So that's all. So this chapter is relatively short, but it's important, but it's also I would say it's easily to understand because we only consider two mechanisms, and this mechanism, I think, in your past learning, you probably already knew some of the drift and the diffusion because that's already widely used in the different courses and different purpose. Okay, so the next one is that we would be interesting because what we actually talk about in previous case is everything in the equilibrium, but for sure that in reality most of the cases are non-equilibrium because of we cannot there's a very limited possibility that the semiconductor will under equilibrium. In most of cases under the transition between the non-equilibrium to the equilibrium. So for sure we have to understand what would be the phenomenon if we consider there's a non-equilibrium excess carriers in the semiconductor. So what does mean the excess carrier? Excess carrier means that if now you consider a piece of your semiconductor material, for example, you have the P-type semiconductor material, but suddenly this piece of the material is being incident with a certain light. So that means you have a certain light start to put on this semiconductor material. And the light can be considered as an external force. And this light sometimes will excite additional carrier in the semiconductor. And this light in the end will introduce additional excess carrier, delta N and delta P. This is that we consider as the excess carriers. And this excess carrier will, at one moment, t equal to 0, generate because of the light. But you can foresee with the time pass by, this excess carrier might be in the end to reach the certain state that all the semiconductor system will reach the equilibrium. So this is a case that we would like to discuss, that what happens if we have the additional carrier being generated, and what happens for this additional carrier, and why this additional carrier in the end will disappear and reach the steady state. So this is a question that we will discuss in this chapter. Okay, so first, just some very basic concept that's related to the carrier generation and recombination. So in the general case, if we consider the band diagram as shown here, we have a top conduction band, we have a bottom valence band, and it is possible to have a certain direct band-to-band generation. So once we have a direct band-to-band generation, that means the electron and hole pairs are created in pairs. So that means that the electron and hole pairs are created at the same time. So there are the two possibilities of the electron and hole pairs can be generated at the same time. The one is suddenly you have a hole generated, but you also create the electron, so you have the electron also generated here. And this is because of due to the direct band-to-band generation. So you generate the hole. You have this one jump to here. At the meantime, you will have the hole generate at this moment as well. And also, there's a possibility that you have the electrons here in the conduction band, and you have the empty region in the valence band, and suddenly these nearby holes will move to this empty region, and also your electrons will be moved to this empty space, and this at the moment that we call the electron and hole recombination. And in this case, this is under the equilibrium. So in anyhow, the generation of the N0, that's a generation of the electron, is equal to the generation of the holes. Gn0 is equal to Gp0. And also, in the right-hand side, this kind of mechanism, the electron and holes will be recombined. That's also equal to Rn0 is equal to the Rp0 at the same time. So this is the case under the thermal equilibrium. So in the end, the generation rate is equal to the recombination rate. So that's a very simple case to consider under the thermal equilibrium, that we simultaneously has a generation of electron and holes, but also at the meantime we have recombination of electron holes can be happen together. So in anyhow, then the generation rate for electron holes are equal to the recombination rates of electron and holes. But these things might become difficult, might become more complicated if we have additional excess carriers. So once we consider these excess carrier generation recombination, then everything will start to become a little bit complicated. The electrons in the valence band might be excited into a conduction band. For example, there is a high energy photon incident on a semiconductor material. So that means original we have the N0 and P0 here. But now due to these additional high energy photons, we start to create additional excess carrier, which is delta N plus and delta P, because this generation is simultaneously for the electron and holes together. So in this case, the total electron concentration start to change. This will become N is a total is equal to the N0 plus delta N. Right? So I think so far still very easy to understand. At the meantime, similarly, our P is equal to P0 plus delta P. So that's the same. So with considering the high energy photons incident on our semiconductor material, we can consider the generation rate are the same. The reason why we put the prong here is this is a generation rate for the excess electron and holes. So that's why there's a prong on top here. But because this material will be incident with a photon, so the generation for the additional holes and the generation for the additional electron are the same. So therefore, our GN prong is equal to GP prong. And now our N total electron concentration is equal to N0 plus delta N. And total concentration of hole is a P0 plus delta P here. And then what we have to worry here is that this additional excess carrier, because nowadays we found out that this is no more in the equilibrium, because in the equilibrium we only consider N0 and P0. So under the equilibrium case, we all know there's a very well-known equation where our N0 times P0 is equal to Ni squared. So that's only valid at the equilibrium. But now we are not no more in the equilibrium. So in this case, our N times P is no longer equal to N0 and P0 anymore. And this one is equal to here. So that means in this case, N times P is no longer equal to the Ni squared anymore. So that's the situation that we want to discuss. And also, this electron in the conduction band might fall down into the valence band, lead to the process of the exact electron and hole recombination. So that's the case here. So this is excess electron and hole recombination. So now we are in the new questions that once we have the additional electron and holes, and then what will be the situation we need to figure out how to solve these questions. So now we have to do the step by step. The first one is we are interested to consider this total electron concentration versus the time, because we expect that there's additional excess carrier being generated in the semiconductor material. But we can also foresee possibly this excess carrier will not stay for very longer time. So now we have this one. We have the this is a material. We will talk about this later. So first we use this one to describe that because of this additional excess carrier might not be able to stay forever. So this excess carrier has a time dependency. So that means in the end, our total electron concentration also has a time dependency. So we have a time dependent of the total N and then the total P. And then the first question we are interested in is this time-dependent correlation with respect to the time. So therefore, we can have the following calculation that the nt over dt. So this means this is we are interested in the rate, right? This is the nt over dt. We are interested in the nt over respect to the time, which can be expressed as the following. Which can be expressed as the following, that we have a certain constant value that we call the alpha r, and then the Ni squared minus Nt times Pt here. And how do we understand this equation? You can simply consider that if everything go back to the equilibrium, that means Nt Pt will be equal to N0 P0. And then Nt Pt equal to N0 P0. This one will be equal to Ni squared. So this one and this one, in the end, this will become a 0. So that means this equation is valid, right? Because then in the end, once go to the equilibrium case again, your change rate for this NT is becomes 0. So I think that would be more easy to understand the meaning of this equation rather than to figure out that how this equation coming out, because this equation coming out with lots of the assumption. But I think if you come back with a certain user result to understand that in the final goal in the ultimate case that your NTPT will be equal to N0 P0. This will be equal to Ni squared. So this one can be will be equal to 0. So that means that this rate is equal to 0. So that's the case of equilibrium. So this is how this equation is coming out. Okay, so then we just try to expand this equation. We put everything here with this equation. Then we get this very complicated show me here. But now we have a certain assumption to simplify the case. We'll consider this is a p-type material where our P0 is much larger than N0. I think that's pretty makes sense. This is a P material, then for sure your hole concentration will be much higher than the electron concentration. But another assumption is what we call the low-level injection, where our additional excess NT will be smaller than the P0. And this is condition we call the low-level injection. This is condition that most of you will be confused. So we have to spend the time to explain what does mean the low-level injection. So like they say here, first we consider this is a p-type material. If this is a p-type material, based on what we know from previous lecture, then the EF will be close to the valence band. Right? But now, so in this case, we can understand that we have the huge hole concentration, much larger than our electron concentration. So let's say we have the 5 holes here. And this is our P0, the thermal equilibrium hole concentration. But then because of our hole concentration is larger than the electron concentration, so we can assume we probably only have the 2 electrons. So this is N0 here. So now if you look at this semiconductor material, we can have the certain categories that the holes, this is p-type material, and then the holes are dominant. So we can consider the holes as what we normally call as a majority carrier. And also, on the other hand, we have an electron, but we only have 2 electrons. So electron, in terms of this whole system, these electrons are minority. So that's why we call, in this case, the electron here are the minority carrier. Just similar to this classroom, I think in our classroom we have more males than the female. So the male in here is the majority. The female in this classroom is a minority. So that's a similar things it happen in the whole system. So in this case, we can consider the holes are the majority carrier and the electron are the minority carrier here. But suddenly, we have the additional photon injected. With the additional photon injected, we all knew there's an additional carrier can be generated, which will simultaneously to generate the same of the delta P and also the delta N as well. But what we try to discuss here is a simplified case. So we want to make sure that our additional electron here should be smaller than total P0, because this still the p-type material, right? But we want to make sure that the additional electron should be smaller than the p-type, because if this additional electron is larger than p-type, then this is going to become a n-type semiconductor rather than p-type, and this is something that we don't want to discuss at this moment. We want to discuss is that this additional carrier won't influence the original doping, will not change the type of the doping. So this additional electron will still smaller than our P0. And in this case, we can still consider this is a p-type semiconductor. So therefore, if our additional electron is smaller than the P0. The P0 here is are the holes, are the majority carrier of the p-type semiconductor. In this case, we call as a low-level injection. Of course, low-level injection is a simplified case. It happened in, I would say, more than around 80%, 90% of the cases that you will meet in the future. But in some very special advanced consideration, sometimes we do have the case where our additional carrier start to larger than our majority carrier. That's a additional minority carrier. So sometimes that's the problem that if you just read the textbook, you will get so confusing. Is because of what they say is that your additional minority carrier cannot exceed the majority carrier, and then that's what they call low-level injection. But once your additional minority carrier exceeds the majority carrier, actually is this one. That's what they call as a high-level injection. In here, for sure, for our basic understanding, we can ignore the high-level injection at this moment. We just focus on low-level injection. But you still need to try to understand the definition and the meaning of the majority and minority carrier, the low-level injection and high-level injection, because in later, some of the very special cases, we will start to talk about, we will use very often as a term of a majority, minority, high-level, and so on, so on. So it's better you get to figure out right now, and that will benefit for your future work as well. So in here, we consider low-level injection. So anyhow, we consider that the additional electrons, additional excess electron won't change anything, because it will be the very small amount compared to the total hole concentration. So our material still will be the p-type. So under this consideration, we can start to simplify this equation and become like in this one. And also the general solution for this one can be shown in here. Our delta NT, our excess carrier generation with respect to time, is a function of the t equal to 0 times exponential minus t over tau n0. And in here, the tau n0 is considered as a minority carrier lifetime. In here, the tau n0 is here. This is P. This should be the P0 here. So this is actually what we call the excess minority carrier lifetime. And also, we can further to calculate the recombination, which is minus derivative of a delta n over t, which will be equal to this one, and in the end will be equal to this one. So this is a recombination rate of excess minority carriers. And normally we will start to get him more and more complicated in the later chapter, but it's good because that means if you can understand the difficult part, that shows that you are toward more professional than somebody else didn't understand this, and this proves that you will become valuable engineers in the future. So that's the path that everyone need to be experienced and then be overcome. And also one more thing I want to mention that in most of the semiconductor, in most of the, I'm not sure for your previous your previous learning in your other classes where the time dependent is some of the concept that you are already get familiar with, or is something that you are not very familiar with. But in anyhow, in semiconductor world, that we are not interested in the steady state case. We are not interested in the static case. We are actually more interested in the time-dependent case in lots of the analysis, because our semiconductor characteristic will be changed over the time. So that's why that in lots of the more advanced learning, we always put the time dependency as one of the factors that we need to consider. So we have a time dependency of generation, time dependent of the concentration. In the end, we have time dependent of the current, and so on and so on. So the time dependency is something that you need to try to get used to this. Okay. So finally, we start to get a little bit sense that once you have additional carrier generated, and this additional carrier will, what does this equation mean? Although the calculation for this equation with some of the assumption might be difficult for everyone, but in the end, this equation is very simple, right? And this equation form exponential minus decay. That's also the very general style that everyone can foresee in the lots of the physics and chemistry. Always has exponential minus something, and this means that our additional generate electron actually will decay very soon, because we have the exponential minus t here. So in a certain time, all of this additional generate excess carrier will disappear, and then we'll back to the equilibrium case again. So this is something that we can start to foresee from this equation. And here is some more detail that I don't want to spend too much time to try to calculate this one. This is just try to let you know that we can generalize, and lots of cases in the end we can have this 1D continuity equation for holes. And also we can have a 1D equation for electrons. Also, with this 1D equation for the electron and holes, and then we can start to further try to have the time-dependent diffusion equation, which we just put everything what we already knew together. We have this current equation, we put inside of this one, and we get the expand for this equation further. In the end, we also consider that right now our NT is not the pure N0, it's actually the one considering the additional excess electron, the one considering the additional excess holes here. So in the end, we put everything together, then we get this time-dependent diffusion equation can be divided by several parts. The first one is something we already talked about, that's the diffusion part. We also have the one drift part, but something new is that now we have to take into account the generation and recombination, and overall this in the end will be equal to this one. So what does this formula mean? This is the derivative of additional excess hole versus a time. So this is excess concentration. Excess concentration versus time. So therefore, we can foresee that this equation is going to tell us that this additional excess carrier has a time dependency. That means this additional excess carrier will disappear in certain time. That's why they have the time dependency. It's for sure. In reality, you can foresee it's not possible. You can only have exponential, positive exponential, and negative exponential, but you cannot have the exponential positive, because the exponential positive means that you will increase towards infinity. So that doesn't make sense. You cannot possibly you inject the additional carrier, but in the end, this carrier will be grow in the end to reach the infinity. That's not possible. But in anyhow, it's only have the chance that this will be reduced and then has an exponential decay. And also we have to use because nowadays we talk about the carrier transport by both considering the electron and then the holes here. So in here we try to generalize the equation that can both describe the electron and holes. That's why we have this what we call the bipolar transport equation. So since the internal electric field creates a force attracting electron holes, this E field will hold the poles of excess electrons, excess holes together, and the negatively charged electron and positively charged holes then will drift or diffuse together with a single effective mobility or a same diffusion coefficient. And this phenomenon is called, so we have to consider that the charged electrons and holes will drift or diffuse together with the same mobility and same diffusion coefficient. And this phenomenon is what we call the bipolar diffusion. and then also the n bipolar transport. So we consider this n bipolar transport, then we can have the equation. This is just the same equation that we described before, but now we can have the define as a term where we call the d prime mu prime here, and then the d prime is a one diffusion coefficient that both consider the electron and holes. And the mu prime is a one mobility that both consider the electron and holes. So this equation is what we call the n bipolar transport equation. And again, in here we consider that the p-type semiconductor under the low-level injection. So in this case, we consider that this is because this is p-type semiconductor, so that's our thermal equilibrium hole concentration is much larger than the thermal equilibrium electron concentration, and furthermore, our excess electron is much smaller than the majority carrier, which are the holes here. So this is a case under the low-level injection. So also has already mentioned the low-level injection suggests that the excess carrier concentration is much smaller than the thermal equilibrium carrier concentration. So this is delta N, and this is our P0. With this consideration, then you will find out that this looks very complicated equation, in the end will become the very simple, just dn. And also, the mu prime is going to become the mu1. So actually, this is a very interesting result because, of course, as I always say, that the first few calculation is always very complicated because we have to use a very generalized equation. But in the end, with lots of assumption, the conclusion is always very simple. But in here, it's very interesting to be realized that if you consider the extrinsic p-type semiconductor, if you consider that this p-type semiconductor under the low injection, in the end, the critical parameter, diffusion coefficient, and mobility coefficient reduced to the minority carrier diffusion parameter value. Which are the constant of for the N-type semiconductor. So what does this mean? This means that now you have a piece of the P-type semiconductor material. But we have the P-type semiconductor, but now we consider that the electron holds everything inside. But in the end, you can completely forget the impact comes from the hole, because in the end, it's only the Dn and mu-n will dominate everything. So the overall diffusion and then the overall transport characteristic of the diffusion coefficient or mobility will actually dominate. Our diffusion coefficient and mobility are dominated by the minority carriers. So here is the point. So I think that's very important. That's why that in the end, the conclusion is very simple. In a piece of material, we have the P, we have the N, we have the holes, we have the mobility, we have the diffusion, we have the drift. But in the end, if we try to consider the most of the case under the low level injection, everything can be reduced as minority carriers will influence the mobility. Minority carrier will influence the diffusion. So in the case of a P-type material, what we actually have to really pay attention is electron diffusion coefficient and also the electron mobility. I think that's the point that we actually would spend so much time try to have this conclusion. And this is also very consistent in the previous discussion. Why, if you ever curious, of course, I think most of you probably haven't thought about this yet, but just let me remind you that in previous case, when we talk about the MOSFET, we already mentioned this is a P-type substrate. And we have the source. We have a source and drain here. And then we have the dielectric here. On top of dielectric, we have the gate. So we already say that the operation of this MOSFET is mainly we apply the VG and we start to have the drain current. And we also mentioned the reason here is a minority carrier. No, at the moment we only say this is electron. But electron here can be considered as a minority carrier because this is a P-type substrate. And here, this is electrons. So electrons here are the minority carrier. So now, even we don't do any equation derived for our current, but probably you can start to get a feeling that the current in here in the P-type semiconductor must be dominated by the minority carrier mobility, which is mu-n. So that's the purpose we described in bipolar transport. Lots of the students, when they try to understand the bipolar transport, they get so much confusing because they don't know what's this correlated in the end to the characteristic for the device. As I say that our goal is try to link everything. Although we have a lot of fundamentals, but every time I try to do my best to intend to link our device characteristics. So this is the purpose that we spend the time to talk about the n bipolar transport, because in the end, what the n bipolar transport tell us that you have a p-type material, in the end it's a minority carrier, which are the electrons dominate. And this is the same thing as shown here. If we look at the transistor as a MOSFET, this is a p-type. And then everything will influence these MOSFET characteristics are the minority carriers, which are electrons. And therefore, the current here must be certain proportional to our minority carrier parameter in here, which is mobility, electron mobility. So here is the main things, the main message you want to deliver in this the chapter here. So also under the N-type semiconductor, we have the DP here. The N-type semiconductor under the low injection, so we have the minority carrier will be the whole, so our diffusion coefficient is dominated by the whole diffusion coefficient, and then our mobility is mainly dominated by our whole mobility. So that's the things. So probably in the beginning, it's very complicated for the equation derived, because we have to use so many very generalized equations. But with some proper assumption, in the end, the conclusion is very simple. That's just as I say already. And then also, this is going to help us to understand the operation of the device, especially in the case of MOSFET. That's why that the electrons in the p-type substrate are very crucial for the MOSFET operations. Okay, so I will discuss the slide, the rest of part in the next week, but I also want to spend the time discuss about something related to the midterm exam. So just a quickly overview. So as we already mentioned that sorry, this should be this should be the 10%. Yeah. So we have two exams. So one is a midterm and one is a final. And the midterm exam is a closed book and final exam is open book. And we have homework 50%. We have the attendance for 10%. So this is something that we already discussed in the beginning. I also want to discuss the time. So original time is planned on the April 21 on Monday, but I hope to reschedule to a little bit earlier, because then we probably will gain some more time that you can prepare for the final exam. But I just heard about that the Monday evening probably cannot fit it, because also in the previous weeks that we need to in previous week I missed one class because I was out for some traveling business trip. So I want to use this time to compensate, and then we don't have to do another time compensate anymore. So I want to use the evening as a time to consider as a mega class, but this evening will be mainly used for the exam. But as I know that there's some of you might not be available on the this time, the 14th is the evening. So I want to propose for the April 15th. So that would be the same time in 6:30 p.m. And then so that would be the Tuesday evening. So I hope that fits everyone. So anyone has a problem for this timing? Anyhow, I want to have the midterm in this week. So if we cannot make it 15, then we choose a 16. If we not can make 16, 17, 18, I hope we won't come on the Saturday or Sunday for the exam. Okay, so I will tentatively put as 15 April. I think so far nobody against this time. So then the 16th, okay? Wednesday evening. 17th. So people who don't come, then I just ignore them. So I will use people who come here as a majority. So 17, okay? So 17 is a Thursday.
Why not Monday?
There's one guy. He cannot come on Monday.
Maybe Friday.
I'm fine. If everyone's happy, and then we will arrange the exam on Friday evening. In anyhow, you need to come up with a time because we still need to make up one class because we missed one class in the beginning, so you still need to make it in the one of the evening. Okay, so 18, Friday evening. Okay? We are all cool, all right? Okay. If you have any question, just let me know. We still have the time to readjust. But in anyhow, it's difficult to find a time fit everyone. So I hope you can make it, okay? Okay, so then the rest of it is a similar location. Ideally, this would be so location will be the same classroom, and then we will have the exam up to the chapter 7, which is non-equilibrium. So I will finish the non-equilibrium in next week. And 60% from the homework example, and this is going to be the closed book exam, as I already say. But we will provide you the equation and the important parameter. So you don't have to remember everything, but most of the important one I will provide to you. And also, you need to have the calculator. So that's a necessary. If you don't have a calculator, you will get a big problems. Okay, so that's all. So we will stop the class, and also the TA. So come. So they will come and distribute back for your homework. So please come to pick up homework. And in the meantime, if you have the questions related to the grading, just talk to the TA. They will explain to you. Okay. So see you all next week.